Welcome. In the previous videos, we discussed how to treat problems in perturbation theory to find the energy levels if we have both non-degenerate and degenerate cases. And now we are going to actually use an example where we have to work with both of those cases and identify which we have to use. So we are going to take the case of the three-dimensional infinite cubical well. Okay, now this is something that I hope you remember from your previous course in quantum mechanics, the first part. I hope you saw it. If not, I will do a very quick refresher. Now the wave function for this, since we now have three coordinates, is going to depend on x, y, and z. And this you can separate into three different wave functions: psi x, psi of y, and psi of z. I'm not really bothering to call them differently. I'm just refreshing very quickly here. And now we know what the wave function is for one-dimensional infinite wells. So now we just have to write it down, but 3 times and multiply them. So we get square root of 2 over a, but cubed, since we multiplied 3 times the sine of nx pi over a. You have to make a difference here between the different n's, since we are going to have 3 of them. Then times sine of ny pi over a times y times the sine of nz pi over a times y. All right, so this is the wave function for the three-dimensional infinite cubical well, and it depends on nx, ny, and nz. And I'm going to put a 0 up here just to make sure that we know that this is the unperturbed wave function. Okay, so now we have this case. And what we're going to do is that we are going to introduce a perturbation. Now this perturbation, h prime, will be of the following form. It's going to be v0 if we are in the region between 0 and a over 2 for x, and for y, so 0 there, and no restriction for z. And it's going to be 0 otherwise. So basically 1/4 of the infinite cubical well will now be filled with this V0 potential. Okay, that is what we are doing here. And maybe I can try to make a sketch. I'm not much of a sketch artist, as you might guess. Maybe I can try. So this is going to be Z direction, X and Y. And maybe we can say that this is A over 2 and this is A over 2. So, well, we have, and this is A. Maybe I'll use a different color here. So the well itself is going to be a cube. Oh geez, okay, it's not. I'm not much of an artist, as you can tell. All right, so this is the well itself, and it will have this this potential that covers 1/4 of it. Okay, it's not the best drawing, but I hope you can get an idea. Okay, so 1/4 of the well, I'm gonna erase it, I'm ashamed of it. 1/4 of the well is covered by this V0 potential. Okay, so let's now find how this changes the energy levels. So let's begin with, of course, the ground state. Now the ground state, well, what maybe just as a refresher again, what exactly are the energy levels for the cubical well? Now the energy levels En of x and y and z, 0 since they are unperturbed, are pi squared h bar squared divided by 2ma squared, and this is going to be multiplied by nx squared plus ny squared plus nz squared, since we have contributions from each one of the 3 directions. All right, so the ground state is the case where nx, ny, and nz are all equal to 1. So we can see that this state is non-degenerate. There's only one energy for this case. And that energy, E1110, is going to be 3 pi squared h bar squared over 2ma squared. Okay, so far so good. So let us now find the first order correction. How did we do that? Well, I hope you remember from one of the previous lectures I did on this course. We can find the first order correction. So maybe I can write it as 1, 1, 1, 1. this is the expectation value of the perturbation, right, sandwiched in between our wave function. So our wave function, it will be psi 1110, and here comes h prime and psi 1110. Okay, so this is what we want to calculate. Now, what exactly is psi 111? Well, let's just go back a little bit. It would be this beast right here, but instead of an x and y and an z, you put in 1, 1, and 1. So let us write that down. So that would be, you know what, I'm actually gonna copy it. I don't really feel like writing it again. I'm just gonna copy it onto a new page. Okay, so this is our beast. Let me remove some of these things, and the ends will have to go away too. All right, that's a smart use of my time. Oh yeah, and I have to write down 1, 1, 1. Okay, so now we have to calculate the correction. So E1110. Oh, sorry. Wait, why can't I Control Z this? Oh. Okay, so this is going to be then the integral of this thing here, complex conjugate, but since it is real, it's going to be the same thing. So it's going to be the integral of this right here squared times the perturbation, which is V0 in a certain range. So it's going to be integral from 0 to a over 2. This is going to be for x. Integral of from 0 to a over 2. This is going to be for y. Integral from 0 to a. This is going to be for z. And now we put everything in here. So it's going to be 2a cubed squared. So we can get rid of the square root. 2a cubed times sine squared of pi x over a times sine squared of pi times y times sine squared of pi. Whoa, that's a y. What? How did that happen? That's supposed to be a z. My apologies. I'm not sure how I did that. All right, sorry. Pi z over a. All right. So now you can see that all three of these integrals are basically the same. The only difference is going to be the upper limit right here. So let's just take any of them. Let's say the integral on x. And let's say that this is going to be, I1. And, almost forgot about V0. Big factor. Don't forget to put the actual Hamiltonian in there. Okay, so V0. Almost forgot about it. Sorry. All right, so let's now solve the integral. So I1, it's going to be integral from 0 to a over 2 of sine squared of pi x over a dx. Now this sort of integral we can easily solve if we write that sine squared of alpha is 1 minus cosine squared of alpha divided by 2, of course considering alpha to be pi x over a. Okay, so let's do that. So we get integral from 0 to a over 2 of 1 minus cosine of 2 pi x over a dx, and all of this times 1/2. Okay, so now we have two parts that we need to integrate. The first is simply 1, right, or 1/2 if we want to include the half in here. So that's simply going to be x. So that's going to be x over 2 evaluated between 0 and a over 2. Okay, that's simple enough. And then we have the integral of cosine. So that's going to be minus sine of 2 pi over x divided by a evaluated between 0 and a over 2 times, of course, because of the chain rule, a divided by 2 pi. Okay, and this sign right here will always be 0, because if we put a over 2 in here, we get 2 pi divided by a times a divided by 2. So we will always have sine of pi. And sine of pi is 0. And if we put a 0 in there, we get sine of 0, which is also 0. So this part is always 0. So we get that this is simply x over 2 evaluated at a over 2, which is going to be a over 4. Okay, and we get the exact same thing for the integral for y. And for the case for z, it's slightly different because we have to plug in a over 2, a instead of a over 2. So in the case for z, we will get a over 2 instead of a over 4. Okay? But the integral is literally the same, that's why I'm not doing it. The only difference is what you plug in here. Okay, so then putting this in here, so one integral goes here, one here, and one here. Our result is going to be, right, E1111. The constant that we had before, so 2 cubed a cubed v0 times, and now a over 4 from the x integral, a over 4 from the y integral, a over 2 from the z integral. So the a's cancel out. 4 times 2 is 8, which is the same as this. So we get v0 over 4. Okay, so that is the correction to the ground state. Okay, that was simple enough. It was a lot of writing, but it wasn't too difficult, was it? Now comes the difficult part, because now we have to maybe just go for a new line. Now we want to address the elephant in the room, because what happens with the second, or with the first excited state actually? Where's the energy levels? Here. Take a look at this, if you will. Sorry, let's get rid of this. Bye-bye. Okay, now what do we have here? The first excited states, let's maybe call them psi A, we will define to be psi 1, 1, 2. Let's define psi B, just to give them names, as psi 1, 2, 1. And psi C, we will define as psi 2, 1, 1. And as we can see, all three of these states will have the exact same energy. So if you plug in 1, 2, 1, or 1, 1, 2, or 2, 1, 1, in either case, this is going to amount to 4. And we're going to get the exact same energy, which means degeneracy, which means we must use degenerate perturbation theory. And what did that theory consist in? So what we had to do was we formed this matrix WAA, WAB, WAC, WBA, WCA, WBB, WCB, WBC, and WCC. Okay, and we knew that we needed to diagonalize this. We needed to find its eigenvalues, because those eigenvalues are the energy corrections to the first excited state. If you don't know why that is, then you must check out the previous video in this playlist, because we explained it there, and it's very, very important that you understand that. Okay, so moving forward, we need to calculate each one of these matrix elements. And as a reminder, we defined Wij, in the general case, as the matrix element, or basically the sandwich here in the inner product between psi I0, the perturbation, and psi J0. Okay, so for example, what would psi AA be? WAA. WAA would be psi A0, the Hamiltonian, and psi A0. So what is psi A? Psi A is psi 112. And according to the wave function, psi 112 would be this thing right here, but this would be 1, this would be 1, and this would be 2. So it doesn't look that bad now, does it? Let me try to figure out where... Damn it, I really should be paying more attention. Just where was I? Here. Okay, sorry about that. My apologies. Okay, so let's now begin. So we want to calculate this. We know that this is an integral, and our wave function is real, so when we integrate with the complex conjugate, multiplying the normal part, it will be just the wave function squared as before. So what we get here, WAA, is going to be the integral from 0 to a over 2 for x, integral from 0 to a over 2 for y, integral from 0 to a for z, all right, and the Hamiltonian in front, of course. Before I forget it, it's just v0, you can move it out. If it had some x, y, or z dependence, of course, you couldn't just pull it out of the integral, but v0 is a constant, so it's all okay. We can also pull out the 2 over a cubed, And then we have sine squared of pi x over a times sine squared of pi y over a times sine squared of pi z over a. But be careful, now it's 2 pi z, all right, because we are in the first excited state. So, well, how does this change anything exactly? The answer is, in fact, it really doesn't. So when we do this integral, we have exactly the same integral as before. So it's still sine squared, sine squared, sine squared. The only difference is that in this case right here, the sine has a 2 in there. But remember, what we did is that we used, okay, sine squared of alpha is simply 1 minus cosine of 2 alpha over 2. So this part right here doesn't change at all if alpha changes. And this, remember, was the only part that survived. So now instead of having this cosine of 2 alpha, we would have cosine of 2 times what we had before. Okay, so instead of having like 2 pi, we would have 4 pi, which is still very much 0 if you take the sine, right? Sine of 4 pi is 0. So we will get, once again, that this part here is 0. You can go ahead and do the integral yourself, but it's literally the same integral that we just did. And the value is actually exactly the same. So I don't think there's much point in going through it in the video. But if you want to, just go back a few minutes and I promise it's literally the same procedure. Okay, so the result then would be the same. So 2a cubed times v0 times a over 4 times a over 4 times a over 2, which is once again v0 over 4. Okay, great. And we can actually see that this is going to be the exact same result that we get for Wbb and Wcc. Because it's simply moving the 2 from here to here, but in all of those cases, the cosine of 2 alpha went to 0 anyways when we integrated, so there's no difference. We get the same result in all of them, which is pretty cool because now in our matrix, we just eliminated or got rid of these 3. That's pretty cool. Okay, so this right here is v0 over 4, v0 over 4, and v0 over 4. All right, so we just got 3 of the matrix elements done super quickly. Now let's move on to Wab. Okay, so what's going on with Wab? Now Wab, this is going to be psi A, h prime, psi b. Well, that's not supposed to be a parenthesis. Okay, we know what psi A is. What is psi b? I'm going to write it down just for you. So psi b is square root of 2a cubed sine of, this is pi x, and x is still 1 here, times sine of 2 pi x over a, sine of 2 pi z, sorry, no, that's not the way it is, it's like this, sorry, pi z over a. Okay, this is the wave function. And please do remember the wave function that we just used for a, did I write it down? No, I'm a horrible person. I'm just gonna write it down here. I wanna make sure that this is clear, so I'll take the time to do it. So for a, it was 1, 1, 2. So it's sine of pi x a, sine of pi y. You know what, my y's and x's look a bit too similar. Pi y over a and sine of 2 pi z over a. Okay, so now we have to do the inner product between both of these. So, and basically between the complex conjugate of the first one. But, you know, it's real, so no worries. But it is important that you keep in mind that in principle, it is the complex conjugate. Okay, so please keep that in mind in case you ever encounter any sort of complex things. Okay, so let's now do this. So Wab, now what is this going to be? This is going to be, take a breather. So let's just put the V0 in front. That's going to come from the Hamiltonian, V0, and times 2 over a cubed. Okay, that's good, all good. And now let's separate each one of the integrals. So from 0 to a over 2 and the x part. So that's going to be sine squared of pi x over a dx. So nothing new here. We already know this is going to be v0 over 4. Okay, we've done this several times already in this very video. Second integral, from 0 to a over 2 of sine of. And this time it's different. Now we have 2 pi y over a times sine of pi y over a. Alrighty. And what else do we have? We have integral from dy, by the way, dy. Maybe let me write it down properly. All right, so dy. And integral from 0 to a of, that's going to be sine of pi z over a. I'm running out of space. Sine of 2 pi z over a dz. Okay, not super neat, but there it is. Okay, so we know the first integral, as I mentioned, but now we have these two integrals where we have this 2 pi y and 2 pi z. We have two signs in there. Okay, that's the point. We have two different signs. So how do we solve this integral? Let me now go to a new page and we can see how to solve it. So let me now maybe define this integral as I1, okay? And we'll solve it. So I1 is the integral from 0 to a over 2 of this dy. Okay, now how do we go about it? Well, what I would do first, just to make this maybe a bit cleaner notation, I would use a chain of variables. Say u is going to be pi y over a, and thus du would be pi over a dy. So dy would be a divided by pi du. Okay, and then our integral would be, I'm going to ignore the limits for now, because at the end I'm going to just revert all of my substitutions and then plug in the limits. If you like to plug in the limits, then you have to change them at every step. I like to do it the way I just mentioned, which is why I will use this as an indefinite integral until I redo all of the substitutions, okay? But it is personal preference. Okay, so this is going to be sine of 2u sine u du times a over pi. Okay, that's good. And now what is sine of 2u? Well, sine of 2u, sine of 2u, this is 2 times sine of u cosine of u. So let's plug it in there. So I meant to change colors here. I1 is going to be integral of, maybe actually, let me pull the constants to the front. So that's going to be 2a over pi. Integral of sine squared of u cosine of u du. And I hope that this is an integral that we have seen before. If not, well, you can, maybe try to figure out or use an integral solver or Mathematica or whatever. But the trick here is to take a look at this and say, oh, you know what? If I derive sine, I get cosine. So I'm going to say, okay, new substitution, I'm going to use v equal to sine of u. So dv is going to be cosine of u du. And that is precisely what we have right here. So by using this substitution, 2a over pi integral, we get v squared dv right away. And that's marvelous. That's amazing. We have now an integral that we know how to solve quite easily. This is simply v cubed, well, of course, with a 2a pi divided by 3. That's great. And now we just have to begin undoing all of these substitutions. So v was sine of u. So 2a over pi, over 3 pi, sine of u cubed. But what was u? No, seriously, what was it? U was pi y over a. So 2a 3 pi sine of, oh damn it, was it 2 pi over, no, I think it was pi y over a. Yeah, pi y over a, yes. Pi y over a all of this cubed, and now we apply the limit. So 0 to a over 2. That was it, right? I believe that it was. Okay, I'm gonna double check. You know, it was an annoying process. I don't want to get it wrong just for that. It was u pi y over a, and that's the limit. Amazing. All right, so let's now plug that in. We get, of course, our constants. And when we plug in a over 2, we get pi over 2. Sine of pi over 2 is 1. So we get 1 minus sine of 0, which is 0. So we get that this part of the integral is 2a over 3 pi. Amazing. So far, so good. Now we have one last integral to solve here, which is the integral of z. And if you look at it, it is the same beast that we just integrated, with the exception that our upper limit is a instead of a over 2. So let's now go to our end result, because there's no reason to integrate this again. Let's just go to our result. Because, as I mentioned, it is the same integral. I do not know where my result is. Jesus. Okay, here. Okay, so here, so what we get now in the second integral is 2a over 3 pi sine of, what do we have here? Well, pi z over a cubed evaluated between 0 and a. And how does this change now? Now we get, of course, the constant in front, 2a 3 pi. But what do we get? Now, when we evaluate a, we get sine of pi, which is 0, minus sine of 0, which is 0. So it's 0, and we are multiplying the whole thing by 0. So Wab is 0. All right. I'm not sure if I feel happy or sad that after all this effort we ended up getting 0. Is it a happy feeling or is it a sad feeling? I never know. But the thing is, it is 0. So let's go back to our matrix. Wab is 0. All right, we made progress, and we actually made more progress than you might think, because what is Wba? Wba is Wab complex conjugate. We saw that in the previous video, right? And you can also see it here. If you take the complex conjugate of this thing, then the ket turns into a bra, the bra turns into a ket, and the Hamiltonian is Hermitian. So Wij complex conjugate is what? Well, it's the same as Wji, which is the same as Wij. Okay, my point is they're both the same. Okay, they are both the same. So Wba is also 0. And it doesn't end there. The marvels continue. Because let's now look at Wac. What would that look like? Wac. Now this would be, of course, Wa H prime Wc. Well, that's supposed to be that. Okay. And what is Wa? Wa we said was 1, 1, 2, and Wc was 2, 1, 1. So when we do this integral, now this here is nz. So that means that we will get the integral of sine of n pi z over a, sine of, this was, oh sorry, this n is 1 here, and 2 pi z over a. And we already solved this, and we know that this is 0. So in this integral, we will get once again the integral that is 0. So Wac is also 0, which means that Wca is also 0. You have no idea how happy it is that we don't have to do these integrals. Oh my god. Okay, so Wac and Wca are both equally 0. And we are now down to 2 final elements of this matrix, Wbc and Wcb. Okay, so now we have to address those 2. All right, and then we are done with this problem, kind of. Well, not quite, but it's fine. Don't panic, don't panic. I'm talking to myself, not to you. Which ones am I looking at? I'm looking at BC and CB. Okay, so BC. So this is psi B h prime psi c. Okay, and what was this? This was psi 1, 2, 1 and psi 2, 1, 1. Okay, that's what they were. So let us now write this explicitly. Wbc, this would be, well, putting everything in, we get the constants, right? So v0, we get 2 over a cubed, and then we have integral of 0 from 0 to a over 2. This is now the x part. Now this right here is simply sine of pi x over a, but now this part right here is sine of 2 pi x over a dx, of course. And now comes the y part. The y part is going to be the same, so it's going to be sine of pi y over a sine of 2 pi y over a dy, and then we get integral from 0 to a of sine squared of pi z over a dz. All right, and now this might look annoying and kind of like a monster, but we actually did every single one of these integrals already. This is the integral that we just solved, and we found its value. The question is, where did I put it? Down. Give me a minute, please. I hate myself. All right, here it is. Here it is. It was 2a over 3 pi, probably. Yes, 2a over 3 pi. That's what it was. So let's plug that in. So instead of just calculating everything over and over, we know that this right here is 2a over 3 pi. And this is 2a over 3 pi. And this part we already calculated in the first part of the problem when we're doing the ground state. So this was simply a over 2. So if we put all this together, we get that Wbc is V0 times, well, that would be 8 over a cubed times 2a over 3 pi squared times a over 2. So here, once again, the a's cancel out, and we have, so this is 4, which cancel out this 2 over there, so we only get 2. So we end up getting 16 V0 over 9 pi squared. There we go, and this is the same as WCB. So, ooh, nice, right? Oh, this is so nice. So this means now, going back to our matrix, that we have now found every single one of these. So this is now 16 V0 over 9 pi squared and 16 V0 over 9 pi squared. But the fun is only beginning, because now that we found this matrix, we are only really getting started with the problem, because we now have to find the eigenvalues. So let us now take this and simplify it a little bit further, because we will have to manipulate it, and of course we want it to be as easy as possible. Okay, so now let's simplify this. We can factor out V0 over 4. So V0 over 4, factor of all of this. So 1, 0, 0, 0, 0, 1. And now if we factor out V0 over 4, we end up with 64, 9 pi squared. Same here, 64 divided by 9 pi squared, and a 1 there. And since these 64, 9 pi squared, they are kind of annoying, we can define a new variable, for example, kappa, or a new constant actually, which would be in this case 8 over 3 pi squared is what Griffiths calls it, you know, just to make it look a bit cleaner. Of course you don't have to, but I mean, it looks better, so you know, why not? So this would be kappa here. It kind of looks like a K, but you know, it is what it is. So this is what we are now working with, and we need to find the eigenvalues. Now, how did we find the eigenvalues of the matrix? Well, we basically had to do a minus the identity times the eigenvalue, right? So 1 minus, let's call it W, minus W, minus W, right? This is just going back to linear algebra. And now the characteristic equation, right? This would have to be 0, of course. The characteristic equation would be, well, by the way, what we can do here, which will really simplify things, is that we are going to find the characteristic equation for simply what is in here, right? Because this constant right here would just stand in the way, and since it is multiplying everything, we can factor it out and we will include it at the end. So our characteristic equation would be, well, the determinant of this. So that would be 1 minus w factor of 1 minus w squared minus k squared, right? This is just going back to linear algebra. So here we can immediately see a solution, which is w1 equal to 1, which is when this part right here is 0. And our options for this to be 0 is that either this part is 0 or this part is 0. And we already found one of the options, so let's move to the next one, so that this right part is 0. So 1 minus w squared minus kappa squared has to be equal to 0. And this is simply, you know, your normal quadratic function. So we get w squared minus 2w plus 1 minus k squared equal to 0. So with the quadratic formula, we can now find two more solutions for w, which are going to be, well, minus b, which is going to be plus 2, plus or minus b squared, which is 4, minus 4 times a, which is all of this. So minus 4 plus 4k squared, and all of this divided by 2. And we can actually do a lot of simplifications here. So we have 4, 4, 4, which we can factor out as a 2, and it will cancel out the 2 here. So we get 1 plus or minus square root of, well, and these two cancel out. So we get square root of k squared, which will be 1 plus or minus the, no, just k. And that is already positive, so no need for absolute values. And there we go. This is going to be each one of the values. So w2 is going to be 1 plus k, and w3 is going to be 1 minus k. And let's just write down here w1 for completion. Okay, so that's going to be 1 plus k, 1 minus k. Whew. All right, we're doing quite well. But now please remember that the actual values are going to be multiplied by our v0 over 4, okay? Because we had factored it out, we need to include it. Okay, so when we take this, the energy itself will be multiplied by v0 over 4 times v0 over 4 and times v0 over 4. So what are our energy levels exactly? Well, our energy levels, so the energy levels for the first excited state. Now, there used to be only one energy level, right? There were 3 different states, but the energy level was simply 1, which was maybe, yeah, let's write it down actually. So the energy levels for the first excited state, right, unperturbed, this was pi squared h bar squared over 2m a squared, and this is plus n squared for each one of those. So it would be 1 plus 2, actually 2 squared. So 1 plus 4 plus 1. All right, so this would be 6. And 6 divided by 2 is 3, so we would get 3 pi squared. Am I covering this with my camera? No. Divided by 2ma squared. All right, so that was our, what? Nope, not divided by 2. That we already got rid of that. Sorry. Okay, so that was our unperturbed energy. But now we have that these 3 states have now split. Now the degeneracy has been broken. So that means that now our energy, including the first order correction, this is going to be, well, this value, I'm too lazy to write it down, plus v0 over 4. This was the case for w1. And then we have E10 plus, then it was v0 over 4 times 1 plus this constant k, which you could calculate it. It was 6, what was it again? I already forgot, 64 divided by 9 pi squared or something. You can calculate that. And then we have this right here, plus v0 over 4, 1 minus k. So what we get is that the degeneracy has lifted. The states are no longer degenerate because of the perturbation. And that is extremely interesting. We will see that phenomenon occur in the hydrogen atom as the form of the Zeeman effect in a future video. And that is really the takeaway here. So I hope that this helped you clarify a little bit. I mean, it is somewhat of a messy procedure, but if we look back, it isn't really that bad. We just had to find each one of these elements which were of this form right here. And sure, it's annoying, but it's doable. It takes some time, but you know, we can get it done. So I hope that I helped you a little bit with this video. If that was the case, make sure to leave a like, leave a comment, let me know what you thought. And please consider subscribing to the channel. It doesn't cost anything, but it really helps me out a lot. So thank you very much for watching, and I will see you in the next video.